You are cruising at 35,000 feet. The cabin is calm. Then a white flash floods the windows, and a sharp bang rolls through the fuselage. Somewhere outside, a bolt of lightning has just struck the aircraft carrying you. Your first instinct is fear. The engines sound the same. The lights stay on. The pilots say nothing, and the plane keeps flying, steady as before. How is that possible? Lightning is a massive electrical discharge, a sudden release of energy between charged regions of cloud, air, or ground. A single bolt can carry 30,000 amperes of current and heat the air to 30,000 degrees Celsius, 5 times hotter than the surface of the sun. That much energy meeting a thin metal tube full of people should be catastrophic, yet it usually isn't. Commercial airliners are struck by lightning roughly once per year each. Some are hit more often. The last confirmed crash in the United States, caused directly by lightning, was in 1967, decades ago. Since then, thousands upon thousands of strikes have hit passenger jets, and the passengers have simply landed and walked away, often never knowing what happened. So the question isn't whether lightning hits planes. It does, constantly. The real question is why it almost never matters. The answer lives in the skin of the aircraft itself, in a principle discovered nearly 2 centuries ago, and in a set of tests so brutal, they involve firing artificial lightning at parked jets on the ground. To understand how you stay safe inside a metal tube being struck by the most powerful electricity in nature, we have to start with where that lightning actually goes. And where it goes is stranger than you think. Lightning does not want to stop inside the airplane. It wants to keep moving. When a bolt reaches a jet, it almost always attaches at an extremity, a nose, a wingtip, the tail. These sharp forward edges are where the electrical field concentrates as the plane flies into a charged region. The current enters at one point. Then it does something remarkable. It travels across the outer surface of the aircraft and exits somewhere else entirely, often the tail or the opposite wingtip. This is the entry and exit principle. Lightning uses the airplane as a bridge, a temporary path and a much longer journey through the sky. Why the surface and not the inside? Because of the fuselage, the main body of the aircraft, which is built largely from aluminum, an excellent conductor of electricity. And here is the key idea. Electrical charge on a conductor moves to the outside. It races along the skin and leaves the interior nearly untouched. This is why the current flows across the outer shell, instead of through the cabin, through you, through the seat where you sit. For a fraction of a second, the entire airplane becomes an electrified surface, glowing at its edges, carrying tens of thousands of amperes along paths thinner than a coin. The metal barely notices. Aluminum handles current beautifully. At most, the strike leaves small burn marks or tiny holes at the attachment points, damage inspected later on the ground. Inside, you feel almost nothing. A flash, a bang, perhaps a flicker. But this raises an obvious problem. Not every aircraft is made of solid metal, and modern planes are packed with delicate electronics that a surge of electricity could destroy in an instant, which is exactly where the engineering gets clever. A modern airliner is not just a metal shell. It is a nervous system of computers, sensors, and wires, controlling everything from navigation to the surfaces that steer the plane. These are fly-by-wire systems, electronic controls that replace mechanical cables with electrical signals. A single lightning surge reaching them could scramble the very brain of the aircraft. So engineers build protection in layers. First, shielding. Sensitive wiring is wrapped in conductive material that guides stray currents safely around the electronics, not through them. The delicate parts sit inside a protected zone, sealed off from the electrical storm racing across the skin. Second, the fuel. This is the frightening part, because jet fuel and electricity sound like a disaster waiting to happen. Fuel tanks sit inside the wings, precisely where lightning likes to strike. So the tanks are engineered with thick skins, sealed fasteners, and careful bonding so no spark can ever jump into the fuel vapor inside. Every joint, every rivet, every access panel is designed to keep the current flowing outside and to prevent any tiny arc from forming where fuel and air mix. Then come the discharge wicks, small pointed rods you can see trailing from the wings and tail. Their job is not to survive the strike itself. Instead, they bleed off static electricity, the ordinary charge that builds up as the plane rushes through the air. By releasing it gently, they keep that buildup from interfering with radios and instruments. Together, these systems turn a violent event into a non-event. But none of this design would be trusted on faith. Engineers had to prove it again and again in ways that sound almost impossible. And the proof came from firing lightning at airplanes on purpose. Here is what most people get wrong. They imagine lightning as a random killer, and they imagine planes as fragile. Both beliefs are backwards. Lightning striking an aircraft is not rare, not unusual, not a near miss. It is routine. It happens constantly, in ordinary weather, on ordinary flights. And the aircraft is not fragile. It is one of the most rigorously tested machines humans have ever built. This understanding did not come easily. It followed tragedy. In December 1963, a Pan Am Boeing 707 was struck by lightning near Elkton, Maryland. The bolt ignited fuel vapor in a wing tank. The aircraft broke apart, and 81 people died. That disaster changed everything. Investigators realized the danger was not the current itself, but a spark reaching fuel vapor. So the entire industry rebuilt its approach around one goal: keeping electricity out of the fuel. Today, before an aircraft design is certified, it must pass lightning testing. Engineers generate artificial bolts, currents of tens of thousands of amperes, and fire them directly at real aircraft parts. They strike wings. They strike fuel systems. They strike the composite materials of newer jets, like the carbon fiber Boeing 787, which lacks aluminum's natural conductivity and needs embedded metal mesh to carry the current instead. They watch for any spark, any arc, any weakness, and they fix what fails before a single passenger ever boards. This is why the 1967 crash was the last of its kind in the United States. Not because lightning stopped striking planes, but because engineers learned to expect it, plan for it, and defeat it every single time. Which brings us back to you, in your seat, watching that flash outside the window. So return to that moment. The flash, the bang, the flicker of the cabin lights. Now you understand what actually happened. Lightning found your aircraft as a path. It attached at the nose or a wingtip. It raced across the aluminum skin, tens of thousands of amperes flowing along the outside, and exited at the tail or the far wing. It never reached you. The conductive shell carried it around the cabin. The shielding protected the electronics. The sealed tanks kept it away from the fuel. The discharge wicks quietly did their work. What felt like a violent event was, in engineering terms, exactly what was supposed to happen. This is the quiet triumph of aviation. Not that danger was eliminated, but that it was understood so deeply it became ordinary. Every jet you fly on has been designed with the assumption that it will be struck by lightning many times over its working life. That assumption is built into its metal, its wiring, its fuel system, its certification. The engineers did not hope lightning would miss. They knew it would hit. So they made the hit irrelevant. That is why the pilots stay silent, why the flight continues, why you land, on time, and walk away with a story you might not even bother to tell. The most powerful electricity in nature strikes your airplane, and the greatest thing that happens is a flash, a bang, and a technician later finding a small scorch mark on the wing. Lightning does not defeat the airplane. The airplane was built to expect the lightning. And that, more than luck, is why you are safe.